Okay, speed and velocity. Here we've got a ball rolling to the right and slowing down. The picture would look like this. We've seen this. We represent it and the model. Well, now I want to talk a little bit about average velocity. Velocity is how far the displacement changes per unit time. And sometimes you'll see a delta t on the bottom. I really just use t. It's the time that for the problem that we're talking about. So we can do different domains of this problem, and each one would have a different answer. Average speed is just distance over time, so I'd have to use distance. We don't do that a lot. Okay, but average velocity, displacement over time. That line over the V is average, which is really, really important. We're going to get to that in a minute. Let's look at the interval from t equals 1 to t equals 4 seconds. From t equals 1 to t equals 4 seconds, the delta x is about 3.5. Okay, 7.5 minus 4. It started at 4, ended up at 7.5, final minus initial, 7.5 minus 4. And notice this is a graph of position versus time. This is not x and y coordinates like in that last slide. So my my average velocity is going to be that delta x, ends up being about 3.5, divided by the delta t, and again, we just use t for that. And that is 3 seconds. 4 seconds minus 1 second. 3 seconds have passed and it's moved 3.5 meters. And so the average velocity is 1.17 meters per second. And what you'll notice is that's also the slope between those 2 points. It's not going to be the slope of the graph when we have a trend line in there, but it is the slope between those 2 points. And that's an important thing. The velocity ends up being the slope of the position versus time graph. So instantaneous velocity is different from average velocity, and we use it quite a bit more in physics. Average is pretty easy to calculate if you have 2 data points. Instantaneous velocity gives more information. Okay, so average, if we just went from 0 to 4 seconds, we said, what's the average over that whole thing? You see, the slope would be the slope of that red line. That's the average velocity. But in fact, that object's almost never going that velocity. Sometimes it's going faster, sometimes it's going slower. Remember we said the slope of velocity versus time graph gives you the velocity. So early on, instantaneous is the velocity at one exact time. We'd actually have to use tangent lines here. So right at the very beginning, that line's going up at that angle. That's very fast. Okay, much faster than the average velocity, much steeper. Towards the end, it's going slower, it's flatter. So we can see the instantaneous velocity. It's going to be a little harder to calculate from a graph, but it's a lot more useful for describing how fast things are going at any instant. We use that all the time. Average velocity, I would actually warn you off of unless it's a constant velocity problem. So here are 2 velocity versus time graphs. These are 2 position versus time graphs. Okay, the blue object's going at a constant velocity because you can see, if we look at the motion map, the space between those dots is the same over same time intervals. Okay, and then in B, it's also constant velocity, but it's a lot slower. It's not moving as far during each time interval. And we can see that in the motion map. And we can see that in the graph because the slope is not as high. Okay, how do the velocities of those 2 compare? Well, the slope of the blue one is 2 meters per second. Unit for velocity is meters per second. Okay, so you can see the slope. Every point on the blue line in the position time graph, every point on that blue line has the same slope. So that slope never changes. So the velocity never changes. It's a constant 2 meters per second. And for green, we can see it's 1 meter per second. Let's try something more complex. Here we go. The blue one, we can see it starts slow. The dots are close together, gets farther apart, gets faster and faster. Okay, and you can see that on the position versus time graph. I'd like that to be a curve as opposed to connect the dots, but I tried to make this slide quickly. Okay, so we can see with the blue, the slope starts small, gets higher, higher, higher. The slope gets bigger and bigger and bigger, more steep. So the speed increases. Okay, what would that look like in a velocity time graph? Looking at the blue, again, it started with almost flat, so almost zero velocity, and then that velocity increased over time. It got faster and faster and faster. Now, look at the green one. I think the green one's more instructive in a way. At the very beginning of the position time graph for green, it's very steep. We look over the velocity time graph, that corresponds to a very high velocity. It's going very fast in the positive direction. Then, as the position time graph gets farther and farther to the right, it gets flatter and flatter. The velocity gets smaller and smaller until at the end it's 0 at 4 seconds. Okay, and absolutely the velocity can go negative. In fact, let's look at that. If that green curve continued to curve and started going down, it would still have positive position, but it would have a negative velocity because it's starting to move more in the negative direction. Okay, and we can do this piecewise. Both of these change at 2 seconds. Okay, the blue one has a negative velocity for the first 2 seconds, right? Negative slope. And then it has a positive velocity for the next 3 seconds. And I apologize, the graph didn't come out great there. The green one has 0 velocity for the first 2 seconds. Then it has an increasing velocity. There we go. So that's a little more like it. Okay, so we can have piecewise behavior of these graphs. And most of the time, our velocity time graphs are going to be linear because that ends up being a constant acceleration. Going between graphs. Okay, well, here we've got a velocity of 2 meters per second for 5 seconds, constant velocity. So we'd say since it's a constant velocity, we know the average. The average is 2, and that equals delta x over t. For t being 5 seconds, the total displacement would be 10 meters. Okay, but I want you to recognize something. That's a delta x. That's a change in x. It's not position, right? We know if it's going 2 meters per second for 5 seconds, it's going to travel 10 meters, but in the positive direction, but we don't know where it started. So this line on the left could be the correct line, or it could be that one. It could have started at position 5 and moved 10 meters in the positive direction, or it could have been down here. It could have started at negative 10 and moved 10 meters in the positive direction. So only information we can get from a velocity time graph is about the change, the delta x. Now, let's take that same problem, and I want you to observe something. 2 meters per second, that's that vertical distance there, or that vertical velocity there. 5 seconds is the time on the x-axis. The area there corresponds to that same thing, and we can actually use this. So the area, we say area under the velocity versus time graph. We really mean between the velocity time graph and the time axis, as you'll see in the next slide. In calculus, we call this the integral of v dot dt. So going between graphs, here's a tougher one. Okay, the first part here, it starts with a velocity of 2 meters per second and slows down to 0 meters per second in the first 2 seconds. Okay, so it's going fast in the positive direction, then it slows down to a stop. It temporarily stops. Okay, well, delta x is the area under, and I say under in quotes because it's really the area between the graph and the time axis. So for the first 2 seconds, delta x is 1/2 times base times height, the area there, which ends up being 1/2 times 2 times 2 is 2 meters. So in the first 2 seconds, it's traveled 2 meters from where it started. In the next 2 seconds, same area but negative. Okay, and the area below, it's traveling in the negative direction, so the displacement is going to be negative. You can think of it as 1/2 times 2 times negative 2, or you can think of the absolute value, 1/2 times 2 times 2, but it's traveling in the negative direction. Okay, and again, it's between the graph and the time axis. That's why that red is shaded in there. Well, that means the total displacement is 0. And here's another way to do it that I've shown right here. Average velocity for a constant acceleration meaning a straight line here. And that's a lot of the problems we have to do with. If that's curving, I can't do it. But if it's a straight line, the average of 2 and negative 2, the beginning velocity and the ending velocity, gives you the average velocity. So the average velocity for this whole trip is 0. Again, I want you to be really, really careful with that. You can only use that equation when it's a constant acceleration, as we'll see in the next unit. Well, if the average velocity is 0, the delta x is 0. So we've found that two ways. One with the area, 2 plus negative 2 is 0, and the other by the average velocity, and the average velocity equals displacement over time. So the graph is going to look like this. It's going to start fast, steep in the x versus time, and then get slower and slower, flatter, and then go negative. So that would be one representation. But again, we only know the delta x is 0. We don't know where it started. So it could be that, could be that. So going between graphs, if you have a position time graph, piecewise we look at the slope at any given time. In calculus we call it dx dt, and that gives us the velocity. So we go from the position time graph to the velocity time graph by using the slope to find the instantaneous velocity. Going back in the other direction, we use the area under the curve of the velocity time graph. That gives you the delta x. Really important that it's delta, it's change in x, it doesn't give you position. And that in calculus is called the integral of v dt.